There we go. Okay. Good morning, everyone. I guess what we can do is, okay, first thing is that no new material today. I figured I'd do a review, and I'm also not going to quiz you guys today. So it just didn't make a lot of sense to do a quiz based on just whatever was remaining. So I'll try to go over everything. What I also did is I looked at quiz responses and which questions people seem to have trouble with. So I have a second deck apart from this one that focuses a bit more on those things. We'll go over that. And then, yeah, if there's anything that I should be spending a bit more time on after today, I'll do that next class or maybe um, a demo, depending on how things go today. I guess in the 1 minute that we have left before other people show up, if you haven't done this, I would appreciate it if you guys could do the evaluation. I mentioned the possibility of incentivizing that with points or whatever, but I am going to be curving the grade up anyway. So if everyone gets 1%, five, whatever, it's like no one's getting 1%. So just this is anonymous, so I don't get to see like what people actually say. They give me like an averaged, smushed composite of whatever you guys say, and the reason I'm sort of emphasizing that you guys do this is because uh, this has been my first time teaching, and sort of going into it, my plan was just to see how things go with class here, and well, I think I had a pretty good experience, and I don't know if you guys also feel like you learned something, and whether you think I should stick with this going forward, because I don't know how I felt about it versus how you guys feel about it may not necessarily be the same thing. So if you think that I'm not um, cut out for this profession, then I'd rather find out sooner than later so that I can, I don't know, pivot to something else, sell my soul and go to the industry. Uh, yeah, so evaluation would be helpful. Um, I know it wasn't perfect, and it was a bit rough around the edges, but I mean, I, I was doing this for the first time, still am, so uh, yeah. Um, I don't know. I just, if you guys feel like I care about this enough that I should stick with it, then I'd like to know that. What I did is I threw pretty much everything that we've covered into Claude and asked it to make a mermaid mind map. So this sort of like groups together things that are related to each other, and just a sort of landscape of what all we've been exposed to. Um, this I will leave for you guys to look at in a bit more detail later in your own time. And if there's anything from this that you would like me to spend some additional time on, I can do that on Tuesday before the final on Thursday. Yeah, so things are just grouped. All of the neural network stuff is down here. Then there's the segmentation related methods, and I'll be going over all of these just long form, but yeah, take a look and let me know. So just overview things that we've seen. We started with just simple stuff, filtering, edge detection, resampling images. We talked about how images end up with holes in them when you're trying to scale them up because we don't have information from there. So how do we fill that? We do that using interpolation. We talked about what makes for good features and how we extract and represent them, what properties of good features would be, and how we can use that to solve problems by finding, by matching them across images. We talked about transforming images in 2D, aligning them by minimizing some distance metric using least squares. Then we looked into using Ransacked. We did panorama stitching. Also looked into recognition problems like classification, detection, segmentation, how we could apply machine learning to vision problems, how to formulate any problem as a deep learning or machine learning problem, and figuring out a good surrogate function to optimize that indirectly solves the problem we care about. Extended that to not just statistical ML, but neural networks. Specifically, spent a fair bit of time on convolutional neural networks and what they do, how we can develop architectures specific to what we're trying to do, how they get trained, why they work, and followed that up with models inspired by the language model paradigm of predicting what comes next in a sequence. We also looked into synthesizing new images using things like GANs and diffusion models. So a bit more detail. Starting off, the things to pay attention to or just be aware of is the image acquisition process in its entirety and how that influences the snapshot of that scene that we're able to take. So properties that influence what the final image looks like would include things like the property of the light source, how bright or what color, whether it's a single wavelength, whether there's a whole bunch, what it's hitting, and the shape of the surface on which that light is incident, and how it reflects it, whether it's uniform in how it reflects light, or whether it absorbs stuff, or whether the reflectance is not uniform over the entire surface. All of those things affect the image that we end up with. Then there's whatever our acquisition system consists of. The lenses may introduce things like spherical chromatic aberrations that show up in the image, and we'll have to figure out how to correct for those with things like camera intrinsics. There's also the parameters that we configure on our acquisition system, in this case, a camera. So setting things like the f-stop, ISO, exposure would all change what kind of an image you end up with. Now that we have an image, we're able to filter those using methods like cross correlation and convolution, which lets us sort of query the image that we're interested in with some predefined arrangement of pixels, which we call a kernel mask filter. And if we're doing cross correlation, it tells us where it's the most similar. We see a bright spot in the response map. And we did that through the context of template matching, where we tried to find where Waldo was. And I think it was an example of a black cat hidden behind like a bunch of stuff. And convolution is similar in how we use it, but we just flip a sign, and that lets us get a response map that shows the result of applying that operation. And we did that to find things like image gradients along XY, and blur an image. There's a whole bunch of things that we can do using that. So what would this do, that kernel? It's emphasizing whatever is below the pixel of interest, and smoothing contribution diagonally downward. But apart from that, it's not some sort of universal kernel that we would bother naming. So just as an example of what kernels would do. So this, when applied to the center pixel, we'd end up with a 3 in that spot because that gets halved. Then we have another 1, so adds up to 4, and then the 8 also gets halved, so 4 and 4, it sums up to 8, and the other stuff we don't care about because it's all zeros over there. Convolution and cross correlation, the operation is identical in how we apply it. It's just we flip the kernel, and applying it lets us see the features that would correspond to that. We were also able to represent this thing as a discrete kernel, which we can apply to images to sort of smooth out contributions in a neighborhood. Gradients, we've used gradients to do a lot of things. Any use cases that anyone wants to throw out that particularly stuck out? Yeah. Yeah. Edges, corners, that helped us build towards feature extraction and sort of debug our initial assumptions of what might make a good feature, and refine our intuition. Gradients are a way to sort of quantitatively analyze drastic changes in intensity values along a certain direction. So we do that for X, Y separately, and then combine that when we do it using our kernels and convolutions. And the magnitude tells us how sharp the change is. And in addition to that, we also had gradient direction. And we were able to build some cool features with that and do some problem solving. One of the first things we did with direction was as part of the, what was it, the Canny Edge detector pipeline, where we were looking at gradient direction and only picking the maximum along each directional vector, which then gave us this, and we called that non-maximum suppression because we were suppressing everything that didn't have the maximum magnitude along gradient direction. We talked about subsampling, so naively just taking pixels, if you're going from full scale to, let's say, 1/8, then you're only, or just if you're going from full scale to half, then you would pick only every alternate pixel. For quarter scale, you only pick every fourth pixel. For 1/8, you only pick every eighth pixel, and that just results in stark differences between pixels, which was not the case in the source material. So the solution to that was to apply Gaussian blur first and then downsample, so that information sort of gets smoothed in the entire image and differences are less stark. Interpolation, there's a few methods to do that. We looked at bilinear primarily. There's bicubic, bunch of others. And nearest neighbor was the simplest one that we started with, where you just look at whatever pixel value would have been closest there and just pick that. And bilinear, what we were doing was averaging pixel values around the pixel that we wanted a value for and using that. Yeah, bicubic looks better, a bit more complicated. So we didn't go into that. The second moment matrix, does anyone remember what this? I don't think I used the term second moment matrix, but we did use the method. This had to do with what was it? The structure tensor and all that was associated with. We'll be going into this stuff in a bit more detail once I get to my other slide deck. So I'll put a pin in that. The Harris operator, we use this to, this, we rephrased it till we got to a point where we wanted to describe structure using eigenvalues, and that allowed us to sort of quantify what is and isn't a corner. And using that, we built our first feature extractor, which was the Harris corner detector. Did we do blob detectors? Feel like we talked about this, but regardless, I guess if we did talk about it, it will come up in the other slide deck. So if there's anything, this is Dr. Snavely's slides, and I feel like I took out whatever we didn't go over, but if this part, I'm not very certain about whether I covered it or not. I feel like I did, but basically what's going on is you have an image, you apply a Gaussian kernel to it, and that sort of smooths it out, and you get to see these regions that you can think of as a rudimentary object detection approach. And this operation, applying it, we use Laplacian or Gaussian to refer to the whole process. So if this isn't something that was covered, then just don't worry about it. And that can be applied at multiple scales, and you get different responses. I do feel like this is something that I ran as code to put in the slides. So if it was in the slides, then just go back and brush up on that. Then, yeah, this, anyone remember what the problem over here was? What's the contents of those two? Yeah, similar enough that you can't really use that to sort of find out where you are within that image. And that's how we motivated the feature extraction and matching pipeline. And instead of just directly comparing pixel values, what we did was a couple of additional steps where we take not just the distance, but also the ratio of distance. And that's how we were sort of ranking our matches when we did panorama stitching and filtering to pick only like the best 20, 30, whatever. I think 50 is what we did in our example in homework. After that, talked about just applying transforms. That was the forward, inverse, and pixel-wise transform operations. You have some target transform that you want to apply, so that involves remapping your pixels. So you pick pixel values from their original coordinates and put them in some new place. And to figure out the address of where we're moving the pixel, we apply our warping operation, which is expressed as a transform matrix that's applied to a pair of coordinate values. And this is applied uniformly to every pixel. So we're able to really succinctly express that operation. And there's a few types of transforms that we've gone over, and what properties of the original image they would preserve. By the time we get to projective, which has the highest number of degrees of freedom, the only thing that's preserved is that straight line still remains straight, and everything else is, all the other guarantees are lost after that. Homography estimation is sort of an extension of the simpler transforms that we looked at. And what we're doing is estimating an equivalent plane, or if you moved your camera to a different place, what would the image look like? That's what we're estimating. So we're able to do that by applying a homography matrix to an image. We also talked about inverse warping, which is you have a pixel in a target location, and we want to get it from its corresponding location XY. So we invert a transform to get it back. Affine transformations were a way to combine rotation and scaling with translations, since translations weren't something that we could directly include as part of the simpler transforms that we talked about. So to sort of accommodate that, we do it using the idea of projection scale parameters. So we're pushing parts of the image farther away or bringing it closer using a third term. And solving for that in the matrix form, okay, where's, we have all of our, so for n pixels, this is how it would be expanded. And there's all the coefficients for this that we just stack, and then multiplying it gives us the new pixel locations. RANSAC stands for Random Sampling and Consensus. What we do is when we have a whole bunch of samples and we want to fit um, a model like a line to it, we randomly choose a bunch of samples, count how many of the samples that we have fit with our candidate model, and do that a whole bunch of times and just pick the best one. Panorama stitching, well, there's a lot to do there overall in terms of what we can project onto, but we looked at the case of just assuming that we're projecting everything back onto a plane, which is this. There's more to it because you can project onto the inside of a sphere, inside of a cylinder, which will let us do more elaborate or complex stitching, like when you have a really wide effective field of view, you can't really condense all of that into one plane, but we know how to do it for something relatively simple. And using RANSAC and homography estimation and feature matching, combining all of those things, we were able to do something like this. The pinhole camera model is one of the first principles of just image formation, and that's pretty much where we started. So given an object, we have an aperture and light passes through that. And typically when we're talking about a camera or something, there's other optics and CMOS sensors. We also talked about the Bayer filter, how we use that to resolve it to an image, but without any of those things, you just end up with an inverted version of the object that you're that's in front of the aperture. And the smaller the aperture, the sharper the image, but also less light gets in. Perspective projection was an extension of the transforms that we've looked at, and it uses the homogeneous coordinate representation where we're taking into account a third scale correlated parameter and using that to remap our images again. After that, we got to the fun parts, in my opinion. I like this stuff a lot better. Image classification was the very first problem definition that we looked into, I believe, or no, we started with segmentation using KNN, but classification is probably the most popular problem to solve, and odds are on the job if you're asked to do something deep learning or ML based, then this is where you'll be starting, followed by, if that works, then you'll move on to something like detection or segmentation, whatever, because this usually involves the least amount of work in terms of preparing the data, because all you need is one label for an entire image rather than having to draw out boundaries or bounding boxes. So we assume that each image belongs to a category, and we learned how to predict what that category might be. Object detection, we care not just about the category, but also where in the image an object of that class is. And we don't make any assumption that there should be only one object of that class. There can be more than one. we looked at just how to partition a sample space into a bunch of clusters, and the simplest way to do that we went over was using k-nearest neighbors. And this is something that I had demoed as well. For pretty much all of the, okay, so k-nearest neighbors had a few parameters that we had to supply, which is how many centers we want. So the k was a parameter that we had to choose going into it, and just what distance we should be using. So just one way to go about figuring out what good values is to just uh, try and see what works. This is pretty much always a part of the workflow. Once you have a working prototype of a model that looks like it's doing something, then you want to try to squeeze as much of discriminative power out of it as you can. So we mess with our hyperparameters, and the way this is typically done is you divide your data set into 3 parts and use this to sort of inform what hyperparameters might work on a completely unseen set. So this is like doing a practice exam before actually taking a final, and then uh, you have not a perfect guarantee, but some sort of assurance that, well, the chances that this will generalize to completely unseen data, as long as it's similar enough to what it's been trained on, that it should do well. This was the overarching principle, which is that you can model pretty much anything as once you parameterize the problem, which is the goal is to find a way to partition a sample space, and you can represent anything that partitions a plane using a bunch of weights. So it's kind of like a way to plot a curve that partitions the sample space for which we use the weights, and optional bias to sort of shift the whole curve in a direction. And that was the underlying approach on which neural networks and everything after that that we were dealing with was built. So once we have some sort of a model, we need a way to estimate how well our model is able to identify things correctly. So we give it a way to identify what it gets right and what it gets wrong by supplying labels and some sort of scoring mechanism that compares the labels with whatever the model predicts, and gives us either a distance or a similarity metric that indirectly we can use to say what our accuracy might be. And then we optimized that. We talked about softmax as a way to represent our raw logic outputs as a probability distribution for classes, depending on how many classes we have. If we have 10 classes, we'll see 10 output values, which all sum to 1, and whichever one has the highest is the probability of that class given the weights and the input. Neural networks, what we care about is the structure and the weights associated with each neuron. What a neural network does was for any input size, we're projecting it to a lower or higher dimensional space that should allow us to separate or partition that sample space a bit more easily. The motivating example we looked at was one where we had a cluster that could be sort of wrapped, fenced within a circle, but we were trying to partition it with a line. So no matter how you move the line around, that wouldn't work. But if you reproject the sampled space, sort of unwrap it, then there's a line that goes through it. So that reprojection of the sampled space is effectively what we're doing when we pass information through a neural network. And convolutional neural networks was one of the first breakthroughs in how we can apply just regular feed-forward network philosophy to the image domain, where we care about sort of spatial relationships of pixels with each other. Because before that, the standard way to go about it was just flatten this image into one long vector and pass that through a feed-forward model. But doing that, you end up losing a lot of this context of what is next to what. So preserving that and also applying feature extraction in a way where you don't have to tell the model explicitly what to look for, whether it's edges or corners, that was revolutionary and a huge step forward. And it also had the benefit of using a lot less parameters, simply because weights are shared. And it's just, if you have 64 filters that you want to apply to an image, then each of those filters gets applied to the entire image. So you don't need one weight corresponding to each pixel, or you also don't need 64 weights corresponding to each pixel, but just 64 times whatever the kernel size is. So if it's 3 by 3, that's 9. And what would that work out to? Something a bit less than 640. Let's see, 580 something, which is far fewer parameters to keep track of than if you had to do it per pixel. So applying that to the entire image, and we're also learning what good filters would be that lets us solve this problem based on how far away our predictions are from what they should be and propagating that backwards. There's still hyperparameter tuning to think about with neural networks. Only compared to KNN, there's a lot more over here, because the architecture itself is not set in stone, and depending on what problem you're trying to solve, different combination of blocks or window size or strides, all of those are things to think about. There's cool little tricks that people came up with, like skip connections that helped gradient propagation forward and backward, and helped us get around the problem of vanishing or exploding gradients and allowed models to converge a lot faster. Then there's just the things to mess around with while training, which is normally you would just set some learning rate and forget about it. But turns out you can start with a pretty high learning rate, and once it gets in the neighborhood of what a good optimum would be, it starts oscillating around that optimum if your learning rate's too high. So there's learning rate schedulers that are part of most deep learning, pretty much all. I don't think there's a deep learning framework that wouldn't have scheduling as part of it, but there's a lot of rules that we can apply to it. One simple way to go about it is just how many epochs you train for, just have some relationship between that versus learning rate and have it decay. We also talked about regularization as a means of preventing the model from just memorizing things, memorizing the training set and what its labels are, and helping it generalize better. There's how to initialize the weights and the loss function. So weight initialization, there's a few methods. The simplest thing to think of is either just all zeros, all ones, random values, but then there's also methods that are named after people who came up with better ways to do it, which are also generally part of things like PyTorch and TensorFlow. And the loss function along with the architecture, hugely important because that sort of tells the model what problem you're trying to solve without, it's a way to represent how close or far we are from our goal. And natural language processing, we talked about just sequence prediction and that paradigm, and queries and keys. And there's the n square computation for n tokens that we do, where self-attention is applied to each token to see how important it is, or how it is related to every other token in a sequence. And we apply the same principle to images by thinking of patches of the image as our tokens. So that allows us to model this as a sequence prediction task and use that to get embeddings of patches. So if you masked a region of this and you had embeddings for everything else, and you said that, oh, well, there's this patch that came first, and there's this, then we don't know what comes here, but we know what comes after it. It's able to predict what patch would come there, since it embeds all of these into some higher dimensional feature space where the relationship is easier to represent. We also looked at how to generate images, beginning with the motivating example of colorizing a grayscale image. So generating the data set was not hard because we already have color images, and we just grayscale that, build an entire set of those, and just invert the problem while we're training it. And that sort of image to image mapping model we use as our generator. And then, since we didn't know what a good loss function would be to say whether an image looks real enough or not, the solution to that was to just add another network that does that for us. And then, using what it predicts, we can improve the generator based on why the discriminator thought that the image was generated. So that works by flipping the predicted class and calculating the loss using the flipped label, and then seeing what the gradients are, and propagating that backwards through both. GANs were able to do cool things. They were able to synthesize faces, or we saw the example of generating building facades. I forget what the model was called, but the problem being solved over there was you have a data set of building facades, and what each region is as a segmentation mask, and invert the problem. So given a component of the mask, what would that look like? What would that arrangement of components on a facade put together, what would it look like? And the high level problem that's being solved is basically learning the entire distribution that the model is exposed to. So, and assuming that whatever else might be expected of the model would still belong to the distribution of everything that it's seen. Colorization was one thing it's able to do. The U-Net architecture, we introduced this in the context of segmentation, because segmentation maps and depth map over here are not all that different. What we basically want is to map pixels to another representation of the same dimensions. So there's a downsampling path where we learn more and more complex features until we're able to represent it as a very distilled composite of complex features, and then use that distilled representation to build back up to the original input dimensions. And there's the skip connections here as well, just to preserve feature maps and prevent losing information once we get to this part. So that's Dr. Snavely's slides. Apart from that, I threw together something, but before going into that, let's just go over this really quick. So this is all the quiz questions. Oh, what happened? Man, I would have liked some more screen space. Okay, yeah, that's better. A few of these. So the keyword over here was homogeneous, where we also have the W term. This is one of the questions that seemed a bit confusing. So at infinity, W is 0. W equals 1 is just whatever plane the object was in when the image was acquired. What else? Translation can be represented by 2 by 2. So if there's any in here that are really off. Oh, and I've made all these quizzes available, and you can take them as many times as you want. And only I'll still have scores from your first attempt. So for practice, you can do it as many times as you want, any quiz. Grayscale. Okay, so I think in here, pretty much everything else was more or less okay. 92. Yeah, this one. Okay, Gaussian pyramid. Yeah, this is. I'll get to this. 82, 92, 88. Okay, so that part is fine. Features. 86, 86, 65. Okay. Yeah, this. I mean. by now I feel like you should all be pretty clear about what makes for a good feature, so I'm not going to dwell on that. Purpose of using the structure tensor. Yeah, this one. So Gaussian weight matrix is definitely not the purpose of doing it. Computing the gradients is one of the steps involved, sure. And what it represents is gradients around the pixels, yeah, to some degree, but the goal was that we use the structure tensor towards corner detection because it's part of the Harris corner detector algorithm, which is why that was the expected answer. Does that make sense? I feel like I can sort of get why this might have been problematic. Maybe I'll just not include that in the quiz grade because I get that it was worded a bit like a gotcha question, I guess, and I don't really like doing that. So this is quiz 2. I'll take another look at it with okay, magnitude of intensity changes. What is so self-similarity along edges and uniform areas would be okay. Low is what we're asking for, and ideally we want high for good features. So what makes bad features is basically what that resolves to. And along edges and uniform areas is what was expected. For each pixel in the patch, weighted sum of gradients and products, Gaussian. Okay, this I guess just eigenvalues and eigenvectors don't get calculated for each pixel, but rather they describe the entire tensor. Characteristics of the corner. This you just have to memorize. Homography matrix is used to transform images. Okay, so that all of that, I think. Oh, intensity. Yeah, this was in there in the slides of what it is robust to and what it isn't. SIFT is good for more things. Fransac does not guarantee results, even if, okay, yeah, you guys got that right. Sorry, lines map to lines. This also you just have to memorize from the book, ideally. Rotation, scaling, translation. Okay, okay, so not bad. Falls. Oh, you guys did pretty good on this one. Reduces, okay. Yeah. Oh, this reminds me. Lucas Canati. How many of you don't have the simplest version figured out yet? No shame in it. Just I feel like I get what might be going on. It's one of the factors that you're not able to test it because it takes a really long time to run. Or okay, okay. Okay, I guess I should have the way I should have phrased that is like if you have taken a stab at Lucas Canati and ran into trouble where it's just taking forever and you don't see anything, One thing I didn't account for when I was making that homework is that some of you might have better cameras than I do, um, and get higher resolution images. So just in terms of doing like for loop computation on it, that's a lot more iterations within loops to deal with. So if you're not able to see your flow map, then just try resizing your image before doing anything with it. Maybe like 320 by 240 or something like that would work pretty quick, and then that should give you like some sort of an idea of what your approach is doing and whether you see any like flow related stuff in it, and then you can take that out once you have it working, or still leave it in but use a relatively higher resolution, because I know some of you have like full HD or whatnot. Mine is not. Uh, and that will really bog you down if you try to do it on the full scale image every single time, especially before you do the iterative or pyramidal versions. So yeah, max pooling reduces the number of parameters by downsampling feature maps, which is where that problem came to me from. Which optimization algorithm introduces a momentum? Momentum. Yeah, Atom has momentum, but momentum-based gradient descent is what introduced it, and Atom has more to the momentum part than just having a fixed momentum value. Purpose of bias, okay. Rectified linear. Yeah, I thought this was pretty funny. I'm glad none of you picked Tangerine. Cosine, which is following are true about k-means, require. Oh, they can only be used for binary classification. No, that's not the case, but I guess I didn't mention that explicitly, that they can be used for other stuff too, so I'll go back and check. SVM. Kernel functions, proctor, to process, true or false. Always require fully connected layers to function, CNNs. No, there's fully convolutional networks also, and like case in point, if you look at UNet, there's no fully connected output layer here, because the final output that we're getting is another image. Fully connected refers to just the regular feed forward type of layer, where there's no convolution going on. So, okay. And then what do we have in here? Instance segmentation. Each pixel is only assigned a class label without distinguishing. So this is false, since in instance segmentation, we cared not just about what class, but also which instance of that class. So you would need more than just a class label. And we do want to distinguish between individual instances, so that would be false. ROI line, okay. So what happened here? Oh, in an RNN, just without any LSTM or any gating. So in gated recurrent units and LSTMs, there's gates that allow us to sort of modify what we hold on to and which positions we should be modifying. So hidden state or memory is not the same as what each unrolled version outputs, but when you don't have any gates in there and it's just a function of previous state and current input, then the current hidden state is basically what it outputs. And uh, output at each, so it's hidden state, and the output at each time step is the same in a vanilla RNN without gates. Self-attention, okay, you guys got that. Discriminator learns to distinguish between real and fake. Generator is the one that generates the fake images. Mode collapse has to do with the generator only predicting like one type of image, even though it's exposed to a whole distribution. Because whenever it predicts that image, the discriminator thinks it's real, or whatever the objective is, the positive outcome is what it gets. So it just keeps doing the same thing rather than pulling from the whole distribution. That is mode collapse. Diffusion is iterative, so it requires more computation. Apart from that, you guys got all of it. Preserve fine-grained spatial information. What is this? Skip connections. Yeah. Just allows for feature extracted at different levels to be retained effectively by the time you get to the end of the forward pass. Increasing receptive field. Okay, this I think is all right. Masking, low res. Okay, what happened here? Depth separable. This I feel like wasn't in there. No. Depth-wise for MobileNet. If there's anything else in here that you think shouldn't have been in here, that wasn't like covered in class, I will I'll reassess and take it out if I think that you're right about that. So let me know. Primary advantages of feature pyramid networks. Pyramids always have to do with multiple scales and sort of combining computation that otherwise would have to be done separately. So just a general rule of thumb to help you figure out what the right choices might be. Multi-scale eliminated the need. Intersectional reunion is invariant to the scale of bounding boxes being compared. Bounding boxes that are predicted, there's no like constraint baked into the model to have it predict something similar to what the ground truth would be, because it's not like the model knows what the ground truth bounding boxes are. And regardless of whether the model thinks that the entire image is an object, whereas the actual object is a small part of it, you can calculate intersectional reunion because I hope this doesn't. Oh, things beeping. Okay, where are we at? Okay, yeah, that's better. All right, so I have an image here, and let's say there's a stick figure cat, and the ground truth bounding box would be something like that. And if your model predicts maybe this, then the intersection would be this region, and the union would be this whole region. So when you divide those areas, you'll see that the union term is larger than the intersection. Whereas ideally, you want them to be similar. So in this case, intersection would be still this region within there, and union would also include that part that doesn't overlap. And they're a lot more similar. So that's sort of what you want to see with intersection over union, because that's just I over U. The areas of so expanding that, this is how would you union would be just the sum of bounding box 1 and bounding box 2, the areas of both of those, and then this is bounding box 1 and bounding box 2. So and union. Okay, switching back, let's go back to our quiz. Feel like that's odd. Oh, right there. Okay. Scale of the bounding box is being compared. Okay, so invariant scale invariance when we were okay, yeah, I didn't really process that. Yeah, that's also a bit ambiguous. Maybe I'll take it out. But so scale invariant metric would be I have image at scale 1 and there's bounding box 1, there's bounding box 2, and upscale and do the same thing. Assuming both the bounding boxes are predicted in the same region when you apply intersection over union at both of those scales, like once you the ratio is still preserved across scales. So that's what the intent of the question was. But I get that. Did that make sense? Yeah. I get the ambiguity. I'll take that out. So, yeah, that's a few freebies, I guess. Um, these things are on my agenda. I just I will be revisiting every graded item. I know you have told me things about your like homework and whatnot. And I have written those things down. I just haven't had a chance to do those things yet. Okay, YOLO is I mean it's in the name. You only look once is because both bounding box prediction and classification is done simultaneously in one forward pass. So it's not two-stage, it's a one-stage, a single-stage object detection model. What else we got? Diffusion is more stable. Okay, yeah. Always and never in options, you should sort of, it should feel a bit sus if that's in an option, because that would imply that there's some sort of mathematical guarantee that it's always going to be higher quality than GANs, which is not the case. Okay, yeah. That took a bit longer than I had anticipated, so I guess it's a good thing I went over that. Apart from that, that gives me some time to refine these, which are more tailored to our material and just quiz responses and stuff. But I'll go over this next class, I guess. It's still a bit unfinished because LaTeX is just hard. Um, as far as the content goes, I think it's okay, but the figures could use work. I could make like I could upload this in its current state if you guys think it would be useful, but I still want to work on the figures. Just a high level run through of the entire course, more or less. Yeah, pyramids. I think the one thing that you guys probably it didn't register is that when we talk about pyramids, the different scales that we calculate and use to do whatever task we're trying to do, these are all computed beforehand and sort of combined into one image. All the multiple scales coexist simultaneously so that you only have to apply whatever convolution just the one time. And you'll get responses at all scales, which is why it's faster when you're doing it like that, because you don't have to do it separately. But it takes a bit more memory because how much memory it takes is each level is about 1/4 the previous one, accounting for them not being divisible by 2. Um, and when you add all of those scales together, it's going to be about 4/4/3 of space. So that's in here, Laplacian pyramid. Yeah, this I don't think we had Laplacian pyramids in here, blobs. Yeah, there's a whole bunch. I guess I'll upload this and you guys can maybe review for the final, and I'll update it once I improve the figures and stuff. So if something feels like it wasn't covered, just feel free to ignore that until I post the updated version. But yeah, most of it's in here. Activation laws. Yeah. Okay. Cool. That's it for today. We only have the one class left on Tuesday before the final, so if there's anything you want me to be doing specifically in class, let me know so that I can prepare for it over the weekend. And yeah, good luck with the homework and project and preparing for finals and everything. I hope you guys learned something over the course of the semester and feel like you understand the visual world through the eyes of, I don't know, electrical engineers and mathematicians and stuff a bit better now than when you first walked in here. And I will see you guys on Tuesday. Uh, Yeah, I mean, since there was no quiz today, and we do have to do one more logically. Yeah, that's the only possibility remaining. So yes, there is a quiz on Tuesday, and it will cover. I'll pull from everything because it doesn't make sense to quiz you guys on just optical flow.
It's 5 in the final. Because you said it's going to cover.
Quiz 5 is a short, like 15-20 minute quiz. It's not a 80-minute exam.
Okay. So basically, they're covering the same things, but just like different time frames.
Yeah.
Okay. Yeah, because I thought it was the last quiz is just cover the lecture 5, lecture 15 to lecture 17 instead of like everything. And then like the final is so like both quiz 5 and the final they're comprehensive. Test.
Yeah, I mean, like you're expected to know whatever has been covered in class. So, and quizzes are never scheduled. So
Yeah, I just don't know if it's just like same as a quiz 4. It's like quiz 4, the note set is only cover like from lecture 11 to lecture 14. So I just don't know for it.
I'm telling you now,
I see.
everything is fair game.
Yeah, I see that. I see that. Expecting. Yeah.
I never said there was going to be a quiz today.
No, I was expecting.
Final exam pattern, how would be
I'm trying to get my hands on older papers. If I get that, then I'll be able to share something. If not, then sharing a sample question paper would mean I have to come up with 2 sets of exams, and I don't know that I'll have the time or bandwidth to do that. But what I can tell you is that it will be multiple choice. You will have to solve some problems. I'm not going to ask any like long form answers. And you get to bring a cheat sheet. Dr. Brata does only 1 sheet. I'm letting you guys bring 2 sheets because I don't want you to have to worry too much about running out of space. So
2 sides or 2 papers?
4 sides, 2 sheets. So
the problems are also going to be multiple choice, right? Like, we need to solve out something.
You will have to solve stuff on a scratch paper, but the final answer will be multiple choice. And yeah, you don't really have to memorize any complicated formula, just know the basic transforms and things like that. Yeah.
What about the time exam? Like, how much duration will be that?
So our normal class is scheduled for 80 minutes, right? 10:30 to 11:50. So either an hour or maybe 75 minutes. But yeah, you guys should definitely be here at about like 5 minutes before class. And I'll also put out a seating arrangement. So yeah, work out the details and post on Piazza before the final.
ST3, I had a problem with the lockdown. So I just was writing the exam.
You did both there and paper quiz, right?
Yeah.
Yeah. I know about that, and Hima told me about that, so we're considering a paper quiz.
Okay.
Yeah.
So because it was not updated in the grade.
Yeah, there's a lot to do, and just I haven't had a chance to just comb through all of those things, since this also takes a lot of time just to come up with. Yeah.
Four, I'm not able to understand what we need to work for the pyramidal flow. There's a warp image function that you have given.
Mm, is that in pyramidal or is it an iterative?
Was given before pyramidal.
Uh, I'll have to go back and check that. Mm, mm,
Start from the courses level and we go to the final level.
One second. Mm, so warping was okay. I guess I should have moved that function a bit later. Warping, as far as I know, from what I remember, one second. Convert images, grayscale, build pyramids, initialize flow from courses to finance, not compute at the current level, overall flow estimate, final, yeah. And in iterative, so warping is required for iterative, but not for pyramidal. Because in iterative, what you do is estimate flow and use that flow estimate to warp your second image um, back to where the first image should be using flow. So you know how contents in the first image moved uh, from first to second. That's what your flow represents, right? And then if you use flow to invert the second image, that should bring you back to the first one, but it doesn't. So then you
Again, we find the
refine it. Yeah, that's what the warping is for. So you don't need it for pyramidal. That's just a flaw with the way I organized
there
it.
was
So I'll,
something called just I don't understand how do you adjust pyramid? What do you mean by adjust?
uh,
Or
could you post on Piazza with like screenshots of the sections or maybe line numbers or something? That it's a bit hard to like switch gears right now. But I'll look at it and reply to you later tonight.
also, do we need to incorporate this implementation into that?
That's not a graded
Okay, so only the
aspect
playground is
of it.
graded, right? Because it takes too
Uh,
much time to do run this. So when I do it,
Only like once to run. What are you talking about? The playground or?
no, the application.
Yeah, that like I get that there's a lot of variation in what people are running it on, and there's GPUs, no GPU, there's different camera resolutions, all of that. So
I implemented the initial version of it and tried to do that, run that application with that.
yeah, with the initial one, you'll have a very hard time just because of how long
Even
it
the
takes to
iterative
do it
also
for
takes a
one.
lot of time. So I was thinking combining them would also be time consuming real time application.
Yeah, if it's prohibitive, then you don't have to. But
Okay, so
as
only the
long as
playground is graded.
yeah, you're welcome. Just give me 1 second. Okay, yeah.
This is based on the entire service or it's just doing some.
The only sort of constraint I've ever applied to quizzes is that I don't ask if whatever was taught in a previous class, if it was new material, I try to avoid testing you guys on things that are very fresh. But now that we're close to the end, I figured if I gave you guys review material and then quiz you on that rather than on just optical flow, that will be of more value towards being prepared for the final. So everything's going to be on there. But since it's an in-class quiz, yeah, it's not going to be very like rigorous, and I'm not going to ask you like weird big questions or anything. Just whatever the regular quizzes are like.
Use Notex only for Vita kind of or can you Word as
Homework for Word is fine, yeah. That I was adapting the older problem statement, so I left that part in. The project report needs to be in that format. That's all. Um,